Hello, I'm Shravanti. I'm a PhD student at the Indian Institute of Science. It's a pleasure to present our work titled Boosting Adversarial Robustness Using Feature-Level Stochastic Smoothing. This is joint work along with my colleagues Samyak Gaurang and Professor Venkatesh Babu. Deep neural networks have outperformed the best of classical methods in many fields such as computer vision and natural language processing. However, they're susceptible to adversarial attacks, which are carefully crafted imperceptible noise, which can lead the model to confidently misclassify images to completely unrelated classes. Two of the well-known methods of protecting systems from such attacks are adversarial training and adversarial detection. Adversarial training improves robustness and reduces sensitivity to random and adversarial perturbations. However, the current state-of-the-art methods achieve only about 50% robust accuracy on CIFAR 10 on ResNet 18 architecture. On the other hand, adversarial detection methods aim to detect adversarial examples and abstain from prediction when such examples are encountered. This boosts the accuracy on accepted samples, but the training process could increase the sensitivity of the network to random noise. We find that state-of-the-art adversarial detection method CCAT rejects more than 95% images which are perturbed with very low magnitude Bernoulli noise. In fact, the accuracy of even a normally trained model on such images is more than 90%. In this work, we aim to bridge the gap between adversarial training and adversarial detection methods by improving robustness to the best possible extent and rejecting images which cannot be correctly classified. An implementation of the proposed feature-level stochastic smoothing classifier is shown here. Similar to the VAE formulation, we enforce the encoder to predict the mean and variance vectors for each input sample and use the reparameterization trick for ease of backpropagation. The sampled feature vector is passed as input to the multi-layer perceptron for final classification. Every sampled feature vector gives a different random prediction. This architecture enables sampling during training and inference. Feature space decision boundaries of standard classifiers tend to be highly non-smooth, leading to poor generalization. In the proposed method, we generate predictions by taking an expectation over randomized feature vectors, leading to smoother decision boundaries and hence better generalization. We now look at the adversarial training procedure. In the first step, we train on adversarial samples, which are generated by maximizing cross-entropy loss using 10 PGD steps and 1 adversarial weight perturbation step. We minimize the cross-entropy loss on perturbed samples and the KL divergence between the softmax outputs of the adversarial and clean images for adversarial training. Similar to the VAE objective, we minimize the KL divergence between the Gaussian distribution corresponding to the clean and standard normal distribution. We also minimize the KL divergence between Gaussian distributions corresponding to a pair of adversarial and clean samples. We next train the network on clean samples with similar losses. Using the proposed approach, we achieve significant improvement over the baselines on CIFAR 10 and CIFAR 100 datasets. By varying the rejection threshold, we can achieve the required trade-off between boost in accuracy and the percentage of clean samples that are correctly classified and rejected. We achieve improved results over baseline across a wide variety of wide range of threshold values. To conclude, we propose adversarial training using a stochastic classifier, which enforces one of the feature layers to follow a predefined distribution. The proposed algorithm helps achieve a boost in adversarial robustness over standard deterministic classifiers. By rejecting low confidence samples, we obtain a significant boost in adversarial robustness. We propose metrics to evaluate classifiers which combine adversarial training and detection. Finally, we propose a scheme of combining our approach with adversarial detection methods such as CCAT to achieve the merits of both. We look forward to meeting you during the Q&A session. Thank you.
Thank you very much for your talk. The next paper is ID10, presented by University of Science and Technology.
Hello, I hope you can hear me.
Yes.
Oh, now I can share the screen. 1 second. I hope you can also see the slides.
Yes, we see it.
Perfect. So hello all together. My name is Joanna Jaworek-Koriakowska, And I would like to present our work entitled SafeSO, Interpretable and Explainable Deep Learning Approach for Seat Occupancy Classification in Vehicle Interior, which was carried out together with Alexander Kostuk and Paweł Skrów in cooperation with Advanced Engineering Group at Aptiv Technical Center in Krakow, Poland. Oops. 1 second. Okay, so the motivation of our work was straightforward. The detection of seat occupancy connected with belt recognition can significantly enhance the safety of people inside the car. And it has been reported that about 50% of all passengers that were killed during car accidents in 2019 were not wearing the seat belts. Furthermore, the children presence detection is one of the features on the roadmap of the Euro NCAP standard, and it's because of remaining children in the car, and when children are left in the vehicle, it may happen that they even die. Furthermore, child restraints reduce the likelihood of a fatal crash by about 80%. So to address this problem, we have implemented an end-to-end framework based on deep learning algorithm to classify seat occupancy into 7 main categories, including empty seats, seats with everyday use objects, adults in the car, as well as infant and child in the seats, as you can see in the images here. Furthermore, we have also addressed another problem. It's the model interpretability of cases where we don't have the ground truth. We have not the human annotated objects, which are important for the classification. So in our work, we also propose new statistical metrics, which are based on Gaussian distribution and interpretability of GradCam heat maps. We compare the statistics with our outcomes of the architecture that we propose and show that they can significantly increase the accuracy of the system. In our work, we have concentrated on the Spiro dataset, on the BMVX5 model, which consists of over 7,000 different scenarios. Here you can see 3 empty seats, and also the database containing different amount of images. So we also performed data augmentation for this problem. On the next slide, we show the visualization of the problem using the UMaps. You can observe on the left plot the visualization of 7 categories. On the right, the seat occupancy versus empty. And it shows that the problem that we are solving is not trivial, and we are not able to draw boundaries with shallow machine learning algorithm. The streamline of our framework can be divided into 2 parts. On the top, we show the implementation of our architecture, which consists of the pre-trained models. We have implemented or tried in our application the state-of-the-art efficient net models, rest nets, and dense net with adjusted classifier. And in the second step, we have implemented the statistical metrics and tried to adjust them and check how they work for the problem that we are solving. So we got the best results for the efficient net with the Adam optimizer, and we scored about 80% accuracy for the 7-class classification problem. And now I would like to move to the statistical metrics for interpretability assessment. As most important parts of the image and of the problem that we are solving lies in the center of the picture, we are generating 2 different masks based on the probability density functions. So on the second image, you can see that Gaussian distribution. On the third, on C, binary mask, including the central 90% of the probability of the normal distribution, leaving only 5% of each tail. So here are the equations, which you can also find in the paper, and they are also described in detail. And now I move to show you how it works. So the first image is the raw image. Then you can see the heat maps over the image with the true outcome. So it has the correct classification, and the statistical outcome is also above 50%. So it ensures us that the algorithm has concentrated in the center of the image to make the final classification. On the other hand, false classification, we see that the algorithm is concentrating on left and right side, below 50%, concentrating in the middle. So this is false classification. Here we can observe how it can influence the final classification. So about 70% of the images which the statistical metrics showed that were not concentrating on the right part of the image were also wrongly classified. So summarizing, we propose end-to-end CNN-based framework to the seat occupancy classification. We propose new statistical metrics. We perform in-depth analysis of the spheral data set. We perform extensive experiments on the outcomes, and we perform comparison and estimation of the correlation between prediction and model interpretability. Thank you very much for your attention, and greetings from Kraków, Poland. Thank you very much.
Thank you very much for your talk. The next talk is ID 11, which is given by Fraunhofer IAIS.
Yes, hello. Just a second, let me share my screen.
Yes, we see it.
Okay, great. Hi, my name is Julia Rosenzweig. I'm from Fraunhofer IAIS, and I'm happy to be presenting joint work with my colleagues Joachim Sicking, Sebastian Huben, Michael Mock, and Maram Akila on the topic patch shortcuts, interpretable proxy models efficiently find black box vulnerabilities. So in our work, we are interested in uncovering learned shortcuts of a network. So to find spurious correlations that the network relies on for its decision making, but that have no causal connection and can thus potentially pose safety risks. A well-known example for this is the case where a DNN classifies a given image as horse due to the tag. More concretely, in the context of autonomous driving, we want to see whether a given image that is maybe classified as car was classified so based on really meaningful semantic concepts so that the network knows what the car is, or rather on shortcuts. We put all of this in a black box setup where we assume only limited access to the model is available. And this then poses the challenge that common explainability methods that could help to uncover such vulnerabilities are not directly applicable. So we propose an approach to tackle this question by means of using an interpretable proxy network, which is white box, and that is trained on the same labeled data set as the network of interest is trained on. Then we use the interpretable proxy network to find shortcut candidates, and we finally systematically test whether these identified shortcuts also constitute shortcuts on the network of interest, so whether the results then are transferable. More concretely, for the experiments, we use a binary classification task of classifying cars versus no cars, which is derived from semantic segmentation on A2D2. And as interpretable proxy model, we choose a BACnet architecture, which is interpretable by design in the sense that we can pinpoint exactly how each small local image patch contributes to the final decision or final classification. And in particular, the BACnets produce reliable feed-forward heat maps as internal representation, so they really base their decisions on it. This looks the following way. So for each image we want to analyze, we produce the BACnet forward heat map and look for highly predictive patches, so predictive of class car, marked here in dark red. Then we check that indeed it's not a car, but a building in this case by comparing with a segmentation mask. And once we identify this shortcut candidate in orange here, we then augment the original image by placing this patch on top of it in a grid-based manner, but one at a time, and conduct inference with a black box. Basically, what we find is that our patch shortcuts, the examples that you see here in yellow, can effectively fool the black box in a sense that previously the original image is classified correctly as no car, when we augment it with the patch shortcut, it is misleading and classifies it as car. We compare our method against inserting random patches or deleting the semantic content of the patch in various ways. And yeah, we outperform these baselines with our shortcut patches. To summarize, we introduced an approach that can identify learned shortcuts of a black box network and can therefore contribute to SafeML because we can discover such weak spots early on in the development process and could mitigate them, for example, with putting Robustify training on top, similar to adversarial training, or calculating some shortcut exploitation scores that could compare networks' vulnerabilities to shortcuts or datasets feature diversity. Yeah, thanks for listening. And yeah, I'll be happy to discuss in more detail and take your questions in the Q&A session. Thanks.
Thank you very much, Julia, for your talk. So the next paper is ID 12, given by Ruhr-West University of Applied Science.
Good evening. Share my screen. Is it visible?
Yes.
Perfect. So good evening and welcome to my presentation of our paper towards black box explainability with Gaussian discriminant knowledge distillation. Getting meaningful insights to a deep neural network prediction is mandatory to understand their decision. Most approaches explaining and verifying neural network predictions by the presence or absence of semantic concepts require modifications to the base network, which might have affected their performance. In this paper, we propose a method to add concept-based post-hoc explainability to black box models. The key component of the semantic and quantitative local explanation is a knowledge distillation process, which is used to mimic the teacher's behavior by means of an explainable generative model. Therefore, we introduce a concept probability density encoder in conjunction with the Gaussian discriminant decoder to describe the contribution of high-level concepts like object parts or shapes. We showed the effectiveness of this approach by explaining pedestrian detections by means of body part presence. The student model consists of two building blocks, an encoder and a decoder. The additional concept model predicts the presence of each high-level concept and is independent of the knowledge distillation process. Therefore, any pre-trained model that predicts reasonable concepts can be used as concept model. The task of the decoder is to reconstruct the teacher's output by only combining the visual concepts in terms of a Gaussian discriminant analysis. The interpretable classification is given by the logic distribution for each concept. These distributions are generated by the concept model. As the decoder is based on a Gaussian discriminant analysis model and has no trainable parameter, the encoder is used to slightly modify the mean and covariance of the concept distributions to match the teacher's predictions. The encoder itself is based on a deep neural network with soft close activations to guarantee positive variance predictions. To maintain explainability, we use the Kullback-Leibler divergence between the concept logic distribution and the predicted distributions by the encoder. The explanations are expressed as a contribution of each concept to a prediction. The contributions are obtained by the log likelihood ratio between the concept presence probabilities of positive and negative classifications. Positive log likelihood ratios confirm the decisions for a positive target class and vice versa. These ratios reveal the inner workings of our teacher model. Our experiments have shown that the student is able to reconstruct the teacher's predictions while only slightly differ from the regularizer's distributions, which are shown on the right side as dashed line. In comparison, when using only the Gaussian discriminant analysis without the modified distributions, the confidence scores deliver a contradictory confidence value. We used the dense post dataset and the pedestrian bounding box predictions made by Detectron2 to train our student. To match the teacher's predictions, the encoder had to slightly shift the mean and covariance of the high-level concepts food and leg, while the distributions of the other concepts were only marginally adjusted. This can be explained by the bimodal nature of the distributions for the concepts food and leg, which occur frequently in both positive and negative samples. This leads to a deviation when fitting the Gaussian distribution. The correlation between the confidence score when using the predicted distributions by the student increases in comparison to only using the regularizer's distributions. Therefore, we conclude that our framework implements a reasonable knowledge distillation while enhancing explainability without sacrificing the teacher's performance. Thank you for listening, and I'm looking forward to answer your questions afterwards. For more detailed information, take a look at our paper.
Thank you very much. So the next paper is ID 13, which is given by Fraunhofer IAIS and Volkswagen.
Yes, it will be me. So I hope you can see my slides now.
Yes.
And welcome to my talk about common sense reasoning for reliable semantic segmentation, or how to explain to neural networks that plants don't walk on the street. Sorry. Okay. So as we all know, humans understand and reason about traffic scenes using relations among objects. As you can see on this image, for example, we would expect pedestrian to be on zebra crossing. We would also expect groups of pedestrians to be on pedestrian walks or to be close to traffic signals or some traffic signs. But the neural networks that are widely used in autonomous driving currently are purely data-driven, and they cannot employ this high-level knowledge and understanding, which leads to multiple problems. Keeping this in mind, we decided that we want to introduce this high-level domain knowledge to the data-driven neural networks. And for this, you can use multiple frameworks for formalization such knowledge. We selected probabilistic soft logic and decided to try it out with semantic segmentation networks that are very important domain in autonomous driving. So first of all, we have to identify areas for high-level reasoning, for high-level logical reasoning. For example, if we look at this frame, we want to say that these rectangles can contain something that can be pedestrian or something that can be traffic light, and then using the logical rules to conclude if it's true or not. We are using kind of an oracle, the ground truth semantic segmentation, to extract these objects, but it can be anything actually that is more applicable in any case. Then we should construct the set of rules using common knowledge or knowledge of some experts in the area. An example of a rule can be if this something stands on pedestrian walk, and if it stands close to the traffic light, then the probability that this something will be pedestrian is high. The next step that we have to measure the observations and extract them from the data that we have in order to quantify our rules. It can be multiple sources, it can be depth information, it can be color information from the original frame, or we're also using the semantic segmentation done by the network, for example, to understand that our object of interest is standing on pedestrian walk. Finally, we can do the inference of PSL rules, and combining it with the network scores predicted by semantic segmentation network, we can improve the results. Like this, we separated our pipeline into two clear zones where we have sensor level and no high level logical reasoning, and logical level where we have objects and interactions between them. We performed evaluation, checking the robustness of PSA rules to the corruption with different levels of severity. We try to use the corruptions that are very close to something that can happen in nature, like snow or very bright sun or fog or frost. And on the plot, you can see the example for the objects that are classified as traffic signals and how the average score is developing for different levels of severity of corruption. So network scores are really going down when corruption is large. Rules are not so bad. And the combination of network and rules is actually giving really nice results, and it's robust to the corruption supplied to the input images. So we are taking advantage of human knowledge by drawing information from various sources and combining it with data-driven model predictions in order to improve the prediction reliability and robustness via logic reasoning. Thank you, and I'm looking forward to your questions on Q&A session.
Thank you very much for your talk. So the next paper is ID 14, presented by the Universities of Torino and Tübingen.
Hi, can you hear me?
Yes.
Okay, let me share my screen. Can you see it?
Yes.
Perfect. So, hi everyone. I'm pleased to present the paper titled Detecting Anomalies in Semantic Segmentation with Prototypes. It is a joint work with my friends and colleagues Fabio Cermelli, Massimiliano Maccini, and Barbara Caputo. So I'd like to start with a brief introduction on the context of the work, which is anomaly segmentation. And in order to easily understand this scenario, I'd like to start with a simple example. So suppose that we have trained our model and the model has already learned some classes, for example, a car, building, trees, street, and so on. And then suppose that we test our model on a different distribution, the difference from the training one. In this case, an image containing an helicopter, that it is a class that the model has not already learned. So how the model will behave? Of course, the only thing that it can do is to predict the class of each pixel by only predicting the classes that it has already known. So the helicopter will be predicted as a portion of a car, wall, and building. Of course, this is a serious issue because especially in autonomous driving scenarios, being not able to understand that an anomalous object came in front of us can lead to dangerous situation. So what we would like to have would be a model able to actually correctly segment the semantic categories that it has already known, and also being able to understand that some pixel belongs to something, a category, that had not already been encountered in the training, and so could be an anomalous category or potentially an unknown category. So our model starts from an intuition about how we think that the humans consider something as unknown. Something is considered unknown by us when we do not have anything in our memory that can be associated with it. So in order to bring this concept of memory into the model, we used prototypes. A prototype is a mean feature vector of a semantic class and can be seen as a way to encode a class, the feature of a class, into a single vector. So we use prototypes to train the network during train time when we do not have anomalies. And at test time, we use the prototypes to detect anomalies, of course, during inference time. So at training time, we use the image with the label to train the network, and we use the Gaussian classifier that encodes in its weights the prototypes of the semantic classes that it is about to learn. And then at test time, in which in the images of this procedure contains anomalous classes, we use the Gaussian classifier in order to produce an anomaly score. Again, comparing the weights of the classifier, which are the prototypes, with the feature extracted by the network. So we tested our model on SafeSO, which is a popular benchmark for anomaly segmentation. As you can see from the table on the right, on the left, we can see that our model is able to achieve the state of the art. And on the right, we can see some qualitative results. We are here representing the entropy of the network, and we can see that our model has a higher entropy on anomalous pixel, meaning that it is highly unconfident of the categories that belong to those pixels. So thank you for your attention. If you have any question, we will meet at the Q&A session. Thank you.
Thank you very much. So with that, we come to our last talk for this short oral session, which is ID 15, presented by NVIDIA.
Hello. Quickly share my screen. Do you see my screen?
It's still loading. At least for me, it's still loading. Now we can see it.
Okay, great. Hello, everyone. This is Vasu from NVIDIA. So I lead automotive safety for machine learning inference at NVIDIA, and this is joint work with my colleagues at NV Research, Shiva, Tim, and Mandar. I'm going to talk about simulation-driven test and design for safety of AI-based autonomous vehicles. So in a simplistic view, so an autonomous vehicle takes in data from sensors. You have a perception and a localization module, which gives you the world model, which consists of the information about all the static and dynamic objects in the scene. This goes to the planning and control, where you plan a trajectory, and then you have your actuation coming out of this system, right? But if you look closely, then this is not that simple, right? So you have several components interacting with each other, and especially for safety, we require clear responsibilities of each module that are involved in the stack. So the question that we try to ask in this position paper is, what is the tolerance of the planning to degraded perception? So first, one thing is clear. So the perceived world model is always an approximation due to the sensor noise and the perception error. And the amount of error in the world model that's tolerable depends on multiple things, right? So first of all, it would depend on the driving scenario. And I think there was already a nice talk about pedestrian detection, that some pedestrians may not be relevant for safety, while some might be. So the importance of an obstacle from a safety perspective depends on the time to a potential collision with the EV, right? So this is a dynamic problem, depends on the scene, and we try to basically see if, look deeper in this domain and what are the different questions that we need to answer. We understand that these are the key research questions. So how accurate should the world model be, or rather how much perception error is acceptable? Can we use simulation to provide insights to better design the system for efficiency or safety, right? And can we somehow develop testing strategies in simulation for the planner that basically take in realistic error in the world model, right? So we know how the perception behaves, what is error with respect to the ground truth, and somehow feed this in and look at the planner. So this is a figure from the paper, and this is our proposal, which we are also working on. So you start with a particular ODD, and then you do the HARA, like you do in the safety. You derive a set of safety goals. Then you create some test scenarios for this particular scenario, right? And then what you do is you feed this test scenario into the simulator. So we have Drive Sim, which we use, and you can have Carla or other simulators. And then for the state, you would actually inject a particular error and give it to the planning and see how planning actually behaves with this noisy world model. What this would give you is, we call it the safe gamma contour in the paper, which basically characterizes the perception error. And the idea is that this would allow us to create a contract between the perception and planning through safety requirements. So this would give us precise requirements what perception has to fulfill for a particular planning component to behave, right? So you get component level requirements for localization and perception. So we are working on this. So for further details, please refer to the paper. And there's also related work in DSN this year from my co-authors, which is about a safety evaluation framework known as Suraksha. That's all. Thanks for listening. I'm around for questions.